You can see, yeah, okay, you can see it.
Perfect. Okay, welcome back to the session. We have a keynote from Guy Lemieux. He's a professor from British Columbia, and he works with FPGA and computer architecture for a long time. And he's very well known. His scholar has over 4,000 citations. And Professor Guy, please go ahead. The floor is yours.
Great, thank you very much. Hi everybody, it's nice to see you. I had a bit of a camera view of you for a moment, but now I'm just able to see my own screen. So I'm here to talk to you about CX, which I like to think of as the Magna Carta of custom instructions in RISC-V. And I'll explain what I mean by this, and I'll explain what CX is throughout the talk. But before I begin the talk, I really wanted to express a very special thank you to people who've been helping me along the way in this journey with CX, especially with Jan Gray. He and I have been collaborating on this for a long time. We actually started this idea of CX back in 2020, and we had a number of other collaborators, which I should be acknowledging as well, but there's a very long list. But very notable is Jan Gray, and I cannot forget to thank him for that. Also, two of my students, Brandon and Joseph, have helped me explore details and depth into this, and I'll present some of their findings in this presentation. So let's begin. So the Magna Carta. What is the Magna Carta? Well, it's actually a decree or agreement in England, UK, back in 1215 between King John and the barons. And it's sometimes known as the Great Charter. It was originally written in Latin, but there are translations available. The problem was virtually all the land was owned by the king, and the king imposed oppressive taxes, and the king pretty much decided punishment and laws as things were on the fly. And people were increasingly upset with unpredictability of the king and behavior of the king, especially the barons who are trying to run the land and interact with the people. So the barons revolted, and they ended up coming to an agreement called the Magna Carta to limit the power of the king and to transfer power to barons and the people. And it didn't go off perfectly. It was a rocky start. At first, it didn't work out, and they had to redo it and things. But essentially, this is the origin of a lot of modern law and our modern civilization. So it really provides rules for everyone. It is democratizing in the sense that it empowers people to have a certain amount of liberty, freedom of movement, freedom of commerce, and things like this. And it is the basis of many aspects of modern human law, particularly human rights and economic rights. And although not directly related to the free market, it is essentially an underpinning of what evolved to become the free market. And without it, we probably would not have the free market. So this is how I view CX. CX is a democratizing and libertizing effect on custom instructions, because custom instructions are strictly in the domain of a few kings. Who are those kings? The kings are the hardware vendors. They sell hardware, that's their taxation. And the custom instructions in their hardware, these are the king's demands. And you get exactly what the king decides, that's it. And if you want to switch kings, you're going to get a different set of custom instructions, because the kings don't share with each other. They view their demands, their custom instructions, as proprietary advantages. And without sharing and interaction of these instructions, without any common custom instructions, software has no incentive to optimize for just one king. Well, that makes the software vendors the barons. They actually have to appease many kings and pay taxes to those kings, not directly, but their selling of software generates revenue for the kings, generates this hardware sales. For a software vendor to satisfy one king's demand is very expensive, and it excludes other kings. But to satisfy multiple kings' demands, multiple custom instructions, is extremely expensive and prohibitive. They could not maintain that for long. So come along with CX, and CX is what we're calling our new specification or document governing custom instructions. And this is really a Magna Carta-like document that provides power to the people through custom instruction liberty. So a couple of the new things is we now have domain experts involved, and domain experts, they can design domain-specific custom instructions. And we're going to call that set of custom instructions a custom ISA specification, and just for short, we'll call that a CX as well. So CX is kind of taking two meanings here. One, it's the specification, the Magna Carta, but also it's an implementation underneath that Magna Carta of a set of custom instructions. Now, the hardware and software vendors are still present, but the software vendors now write their software to libraries that are written to the CX specification produced by the domain experts. And hardware vendors, they're producing their CPUs, but now they can develop custom instructions also to that common CX specification produced by the domain experts. And hardware vendors don't have to do it alone. They don't have to build their own custom RTL for every CX. They can license IP from third-party vendors and include it in their CPU. And so this gives rise to the ability to produce modular hardware RTL and license it as IP and put that into multiple CPUs from multiple vendors. And this gives assurances, in particular, of the implementation being fully compliant and reliable. Now, one other thing is there can be many different RTL implementations of a custom ISA specification. One can be big for performance, another can be small for compatibility, one could be optimized for low power, and different vendors can produce different implementations of the same custom set of instructions, but they have their own verification process and their own special implementation optimization. So they might be cheaper or faster or lower power compared to others. So this is what we mean by the marketplace and the liberty, is the CPU vendor now gets to choose where to get these custom instructions from. They can design them themselves or from third-party vendors. And these custom instructions can appear in multiple CPUs. So software vendors aren't picking and choosing a single king. They're satisfying just the libraries, and the libraries are written to a domain where the custom instructions of that domain are chosen by domain experts. So it's a little bit more complicated of a system, but it's much more liberty-driven. There's more parties, there's third-party IP vendors and domain experts all participating with the software and hardware vendors. So let's take a look at what this actually means in a RISC-V system. So let's say we have a multi-heart CPU, and I've just drawn 9 here because it fits the box. And I want to add some kind of accelerator. And an accelerator is going to be a set of custom instructions around a specific domain. So here's an example of an image processing accelerator, and it has new instructions that help compute Gaussian blur and convolution. And maybe there's enough room in this extension to put 3 instructions, but only 2 of them are defined. So we leave 1 blank. By enough room, I mean opcode assignment. There's some unused opcodes. So now I could build a CPU, and I can add this image processing set of instructions. And this image processing set of instructions could go into any other CPU as well, any number of hearts. And I could put in one of these CXs into each heart separately, or I could have all of the hearts share a single one. Both implementation options are available. Now, what gets really more interesting is there's going to be a lot more CXs than just one for image processing. We might develop one for communication, we might develop one for bit manipulation, might develop one for cryptography, one for matrix math, and one for activations functions in machine learning, and a whole bunch more. So you can imagine there'll be a proliferation of many different ISA contracts, which each one has a different set of custom instructions in there. What CX allows us to do is it allows each of these sets of instructions to be designed independently of each other by domain experts. So the expert designing the bit manipulation instruction doesn't have to talk to anyone else, certainly not the activation function expert. In fact, they're going to share opcodes. The bit manipulation designer is going to work alone and assign all the opcodes that they want out of the custom instruction space. And the activation function designer is going to design all of those out of the entire custom opcode space. And there are going to be collisions between the bit manipulation opcodes and the activation function opcodes. That's by design. We're going to provide a mechanism to resolve that conflict. There can also be custom CSRs used by bit manipulation and custom CSRs used by the activation function. Again, we're going to provide a mechanism to resolve those conflicts. The point is each one can be designed in isolation. They have complete liberty to use the entire custom opcode space on their own. We're going to impose as few rules as possible on those designers so they can succeed. And the key word now is composability. We want to be able to compose any CX block shown here with any other CX block. So you can imagine I might have a CPU design firm, and I might have my multi-heart CPU, and I might want to add all of these CXs to my instruction set. That's going to be a pretty big CPU. But maybe I want to provide some that are more cost reduced. And so I include only the ones on the left half for one particular market. And then another different CPU that only has the top two for a different market. So I can produce many different CPUs that have many different mixes and matches of these different accelerators. And the beauty with CX is you can produce as many variations of hardware as you want of CPUs. But a single software library, a single binary that someone releases will run on all of those processors without conflict. So it means we have a universal software binary, and it runs whether or not the bit manipulation is present. The software uses bit manipulation internally, and it will search or discover whether the bit manipulation instructions are there, and if they are, it will use them. If they are not there, it'll fall back to regular RISC-V instructions. So this provides a fallback if the accelerated instructions are not present, use slow instructions. But if they are present, you can take advantage of them. Furthermore, you can run on all future hardware that implements those bit manipulation instructions, and there might be faster versions of those bit manipulation logic implementations. And you will automatically run on that faster hardware with higher performance. The one thing that you cannot change is the instruction specification within the bit manipulation instructions themselves. Just like you cannot change the definition of a RISC-V instruction. You can change the implementation and make it faster, but not the actual semantics. So this is the idea behind CX. We want to add multiple accelerators to multiple hearts, have software automatically use these accelerators without restriction. Whether or not they're there, software can try to use them if they're there or fall back if not, so that you can run the software absolutely anywhere. Now, things get really complicated for a number of different reasons. But one of the biggest reasons things are going to get really complicated is if we add state to any of these instructions. Something like pop count doesn't have any associated state, or byte swap doesn't have any associated state. All it does is it modifies an input integer and produces an output integer. Internally, it doesn't need to remember anything. However, things like matrix multiply, if you add a multiply add instruction, you might want to have an internal accumulator. And so you might want to have some memory or internal state. Once you have internal state, these extensions become much more complicated. In particular, as soon as we get into a multi-programmed environment in Linux, we need to worry about different processes that want to share and use these and have context switching between them. So what I'm going to present in this talk is how Linux can share these with multiple processes without any conflict. So we provide full virtualization and full isolation between processes, full security, so that Linux just works. And all of these hardware things are simple to design according to a few simple rules. So let's get started, shall we? Just a note, one of the examples I'm going to use, I'm going to combine these two accelerators at the lower right here, the matrix math and the activation function, in a software example. So as some background, RISC-V, we all know it. It's a great instruction set architecture. And what is the ISA itself? Well, it's a set of instructions which have their semantics associated with the opcode assignment, and a set of CSRs And it's really those CSRs and semantics and instructions and semantics that define the ISA. So when we get to custom instructions, we're talking about not just custom instructions, but also custom CSRs. And so we need to be able to handle the ability for any hardware module to be plugged in and add extra custom instructions and add custom CSRs while conflicting with other plug-in hardware modules, for example. What we really want to do is provide this concept of modularity that RISC-V has in the ISA, but we're going to use a different word. We're going to use the word composability because modularity is, I guess it's a weaker word than the word composable that we're trying to go for, but we're trying to look for very similar things with separation of concerns. RISC-V does have standard extensions for a whole bunch of instructions, and they're great, and we're going to continue to produce those. And what we're going to look at in this talk, though, is how do vendors manage and support the custom opcode space with their own custom instructions. So let's take a look at the RISC-V opcode space. The lower 7 bits determine the major opcode block, and we decode them into this table. We can look at a specific column with 3 bits of the opcode and look in a specific row with another 2 bits of the opcode. And then the 2 LSBs are for instruction size. So according to this, what we want to look for are the custom opcode space. So these are the spaces allocated for custom instructions in RV32 and RV64. So we have 4 particular major opcode blocks, and each of those opcode blocks gives us an ISA space of 25 bits that we can define however we like. That's the custom guarantee that RISC-V has said. RISC-V said, we're not going to tell you how to use those 25 bits. That's up to you. And there's 4 different blocks where you can do that with. Well, with CX, we're going to add a few constraints on what you can do with those 25 bits. And it sort of depends a little bit on whether you want to have modular hardware or not. Or if you're a hardware CPU vendor and you want to produce something completely custom, you can. But for hardware modularity, there'll be some restrictions. I'm not going to go into those precise restrictions now. I think it's a bit too detailed. Let's look at what else we need to make CX work. CX actually stands for composable custom extension. So composable is the word in there that's really important, not really the word custom. And what it is it's an immutable ISA contract. Just like a standard extension in RISC-V is immutable, a CX, once it's published, is immutable. So a domain-specific designer is going to design a set of custom instructions and some custom CSRs, is going to decide what the encoding is of all those instructions and CSRs, and what extra state they hold around, and what the semantics are. And once that's defined, then that's going to form what we call a CX implementation. It's an immutable ISA contract. It's a set of instructions that will never change in behavior. So all those instructions will always be provided together as a unit. And we're going to implement those instructions and CSRs into some external logic called a CXU. This CXU may be physically separate in the logic design, or it may be just ideologically different. It might be scattered around within the CPU design itself. When it's physically separate, it's going to be modular, and we can plug in and remove it in some consistent way using some kind of a instruction bus. Once we have this contract decided, then we're going to identify it with a 128-bit random number. Any 2 128-bit random numbers are pretty much guaranteed to be collision-free by probability. We call these 128-bit numbers a universally unique identifier, or UUID. And this has been used in software component management for decades. You identify a piece of software as a 128-bit UUID, and anyone who designs one will use that same UUID if it follows the same immutable ISA contract. But if they want to produce a different ISA contract, even if it's just a small change in behavior, they would select the new UUID and publish it under that UUID. Now that 128-bit UID gives you a guarantee that those instructions and semantics are present in the current system. So if you're a programmer, what you need to do is you need to use that UUID as part of your software and ask the management software, the OS or runtime system, hey, does this UID exist in the CPU? Yes or no? If it exists, give me an identifier for where it exists in the system. And so this is produced, or this information is kept in a map called the system map. And it'll look up the UID and it'll return what we call a CXU identifier. Think of this like a set of expansion slots in your CPU, where each expansion slot has a different CXU accelerator in it. So you're basically saying, I want to find a specific accelerator. Tell me what slot number it's in, please. And it gives you the CXU ID. So if I wanted to find the matrix math accelerator, I give it the 128-bit value of AA, and then it comes back and it gives me a 0. If I want to find the activation functions, I give it BB, and then it comes back and it gives me slot number 1. And now I'm going to target all of my custom instructions to slot 0 or slot 1. If I run the same software on some other CPU, these CXUs may be assigned different slot numbers because there are maybe different total number of slots, different CXUs composed in total in the system. Not every CPU is going to be able to use the same slot number for everything. So that's why we need to do this map to find out where in this CPU this particular set of instructions is located, which slot number is it. And that's a physical identifier. We don't like physical identifiers very much, so we're going to hide that behind a virtual identifier later. But for now, we have a physical identifier telling us exactly where these extra custom instructions are located. And you can think of this as being an extension to the opcode. So instead of a 32-bit opcode, we now have a 32 plus 128-bit opcode, is essentially what we're saying. And then 128-bit opcode extensions are awkward, so we're going to abbreviate it to a smaller CXUID. That's what we're really doing here. When we ask the software for that map, the software, like the operating system, is actually going to be able to do resource management. And the OS can tell us, oh, it's busy, you can't use it. It's there, but you can't use it. Or no, here it is, go ahead and use it. And that allows us to fall back to regular instructions if it's not present, or to try again later if it happens to be busy and we really want to use it later. So that CXU is going to be doing bank switching of different accelerators and target one of these accelerators at a time. And you do that by writing into a special CSR the value of the selector. And that CSR controls the bank switching. So if I write this physical selector into that CSR, it's going to activate the CXU identified in the lower bits, the CXU ID. Next is the best is to find some status CSRs that help us understand the state of the system. In addition to bank switching between different accelerators, each accelerator can have internal state. And for generality, we allow more than one copy of that state for independent use. So we have one copy of the logic, like the ALUs, but we might have completely different copies of extra register files, for example. And those are state contexts or state IDs. Those are extra bits on the selector. So we select between which accelerator and then which state context in that accelerator to use. And you see in this example, we have 8 bits for CXU ID, allowing us to connect up to 256 different accelerators in a CPU. And we have another 8 bits or 256 different possible state contexts per accelerator. So it's a vast space of possible state and accelerator usage. We're going to provide virtualization and protection or isolation between processes by hiding these physical identifiers, the state ID and CXU ID, in the operating system so that the application layer, user level, cannot touch them. We're going to provide a level of indirection, much like a page table, but we're going to call it a selector table. But this is the raw physical format that you see right here. All 4 of these things defined in the draft 6 specification that we have are part of the ISA that we're adding to, the RISC-V ISA. In addition to that, we also have looked at changes to the calling convention and ABI, and an optional physical logic interface. And these are non-instruction set components that are also covered. They have the calling convention provides an optimization to software and the use of legacy instructions. And the logic interface allows us to do modular insertion of RTL for hardware for custom instruction IP. So I'm going to spend most of the rest of this talk on items 1 to 4, where we talk about bank switching and the state context and the virtualization. In terms of virtualization, the way virtualization works is we're going to produce a table in memory, and it's going to be exactly 1 page in size, 4 kilobytes. And it's going to be in operating system protected memory, so the user code cannot read or write this table, only an operating system can. And those physical IDs, the state ID and the CXU ID, they're going to be stored in this table. That's going to be the target of our custom instructions. We select a particular CXU and its particular set of state to operate on. And this table has an index offset from 0 to 1023, so there's up to 1024 different entries in the table. And we can use those index values as a virtual index or virtual selector. So the application layer, the user level, is only going to see the index. It's going to say, I want to access accelerator in slot number 2. And then inside slot number 2, the operating system is going to have assigned to it state ID 0 and CXU ID 1. And that corresponds to the activation functions. That assignment is a table construction. It happens in the operating system when you do an open, and it's going to be removed from the table when you do a close. So there are going to be some function calls in the OS, open and close, to add and remove things from this table. And this table is exactly 4 kilobytes, so it fits in a single virtual memory page that gets marked as OS only. So it's protected by the virtual memory system. Users can generate any index that they want in their virtual selector. That's the user level code. Anything from 0 to 1023. However, although they could generate any possible index, there will be lots of entries in that table that will probably be marked as invalid by the operating system, and they will just end up resulting in an exception to be generated as soon as you try to use it. Only things that have been previously opened will be accessible in the table, and so you're guaranteed to have access only to the things that you already opened. You can't access anything that's been opened by any other process because they're not in your table. Those will be located in the other processes table. So this table is unique per process. And by keeping this table separate per process, the operating system enforces the isolation. Also, there's something I'm not going to talk too much more about, but in this index 1, for example, we see that accelerator 0 has state 0 assigned to it. The operating system could assign another row 3 to 0, 0. And what that would do is it would give 2 different copies of the state context in the user land, but in the hardware, there's only a single copy. And so the operating system would automatically do context switching whenever the user switches between selector index 1 and selector index 3. And so it would save and restore all of the accelerator state in between those uses without the application actually knowing that that was going on. And that's really important because we want to have separate software libraries, like an internet library and a computer vision library and a machine learning library, to possibly use the same accelerator, but have independent copies of their own state in the same user process. And that's an essential feature. So the net effect is we have this isolation and protection enforced at the operating system level, and this inability to access the state of other processes, even though they're physically in the system. We cannot generate direct physical pointers to them because it goes indirectly through this table managed by the operating system. So that's sort of the hardware specification for CX. But what's missing so far? Well, we don't have an actual programming model around this, and there's no actual model for managing the state, which becomes important in the runtime and operating system. So we need an API and a model for managing the state. So let's talk about that. In order to talk about that, let's talk about a use case, provide an example. So suppose I have some program that I'm writing, main.c, and here it is. I'm going to go into detail as I step through this. So I have two includes for two different accelerators that I want to use. One to do power computation and another to do multiply accumulate computation. So I'm going to include the function prototypes for those two headers. Then I'm going to do some computation, and I'm going to do it in a loop. I'm going to call something for power, and I'm going to call something for multiply accumulate. And then when I'm done, I'm going to close those. But let's see what happens when I try to call the power function. And this power function is going to have two versions, an accelerated version and a not accelerated version. So in the POW library, the code on the right is shown. And if I walk through that, what I have is I have a myPow function call, and it's going to go into the library. And the first thing the library is going to do is it's going to say, hey, has this accelerator been opened before? If not, let's try to open it. So the opened before is the if cell is less than 0. And cell is initialized on -1. So initially that's always true because there's no selector, and the negative selector is always invalid. In that case, it tries to open the accelerator by giving it the 128-bit UUID that's necessary to access that accelerator. And this is an operating system call. The operating system looks up this 128-bit UUID in its system map, and it comes back with that 8-bit CXUID. It's also going to assign it a state context and return that as part of a virtual accelerator, virtual selector. If it turns out no accelerator is available because it's simply not present, or it's in use by too many other functions, other processes, and unavailable, then we'll receive an invalid selector and it'll remain set to -1. In that case, if it remains set to -1, we will fall back and do regular software instructions, regular RISC-V without acceleration. Otherwise, what we'll do is we will try to use the accelerated instructions. So we'll select the selector. Now this activates all custom instructions in the future to go towards this CXUID. And then all custom instructions go to that CXUID, and we give it an opcode and parameters or operands from the register file, and it produces results. When we're done, we want to restore use of regular custom instructions that are not part of CX, so anything legacy that hardware vendors produced, and then return back to the main function. The next thing is we call a different function in a different library entirely. And you'll notice that in myPow, the selector has been cached, and the next time we use it, cell will have automatically been kept as a positive value, and we'll skip the open it and go direct to selecting and using the POW function. Similarly, my Mac will do the same thing with the multiply accumulate. Then when we're done, we have to close out anything that we've opened. Also, at the end of a process, these will automatically be returned to the operating system. So we have an open function call, and this open function has to do a number of things. It has to look for the UUID if it's present in the system map. It has to see if we're going to allow permission to access it for the task. These are, maybe some accelerators will not be granted permission, but to some users. And then we need to allocate system resources and initialize the hardware context and so on. The other API calls that are important are select to activate a selector, and close to return the resources, and then a status check, which also serves as a fence to wait for the completion of custom instructions. This brings us to a possible problem. We want to have many different libraries using these accelerators, and we don't want to worry about conflicts between them. So if we have library 1 and library 2 and a main program, and they all want to use a crypto accelerator, how do we enable that? Well, how do we do that for the register file, regular integer register file? We would save it on the stack before calling a function in the library. Well, we don't want to start messing around with the stack and putting a bunch of accelerator state on the stack. That would be a large amount of state to spill on every function call. Also, we want these things to be compiled separately, so we don't want one to have to know about the other and save and restore things from that point of view. Ultimately, the problem is you're going to have more libraries than there are physical contexts in an accelerator. And so we need to be able to share these contexts within a process. This is called intra-process virtualization. And then, of course, in a multi-program system, we're going to have multiple processes running at the same time, and we're going to need to have sharing of those accelerator states between processes, or inter-process virtualization. And we can do both of these things with CX. What we're going to do is time share the state that's stored in an accelerator. If there's just one physical context, we will time share it between everybody. But if there's multiple copies, then we can have some that are shared and some that are exclusive for performance. And that's an operating system driven policy decision. Ultimately, though, all of the switching will be automated and the user won't have to do anything except indicate when they open it what their preferred policy is from a performance point of view. The other thing is we're going to have to select between different accelerators, and we want that selection to be fast so we can rapidly switch between two accelerators that might be both used inside an inner loop, for example. And so how are we going to make CX select fast? Well, what we don't want to do is we don't want to have to save the state all the time every time we call CX select. So instead, actually, I'm going to skip this for time reasons. And I'll skip this for time reasons. I want to make sure we finish. So what I just skipped is an alternative way to implement it other than that 4K table, which is a little more compact and good for embedded systems. And this has just been submitted and accepted to FPL 2025. So there's a paper I can send to you on that alternative lighter weight for embedded systems use. So let's go to the API performance. Now we don't have this running in hardware, we have it running in QEMU. So we use instruction counts as a proxy for performance. And our open and close calls take about 1,400 and 460 instructions respectively. These are both system calls. An empty system call in Linux for RISC-V, I believe, is about 200 instructions. So these are, including those 200, all the instructions in total needed. The select call, in contrast, requires only 2 instructions and is not a system call. It's composed of a load instruction followed by a CSR write instruction. And then to do context switching, custom instructions are going to need to trap once in a while, and the trap handler takes 683 cycles. Not cycles, instructions, sorry. These instruction counts may increase, in particular as the system is used and some of the OS management data structures are filled up and searching and things take longer. So it'll take more instructions. And also, if the accelerator needs a larger context to be saved and restored, it's going to need more instructions. These counts are for a context of one word. In the embedded version that we produced for the FPL paper, we can actually use fewer instructions for open and close. However, it takes more instructions to handle custom instruction trap simply because there's some bit masking that needs to be done, and bit masking in RISC-V is not very efficient. So that's a Linux implementation. We also have a bare metal implementation where we get rid of a lot of the Linux overhead, and you can see that open and close are actually quite efficient in bare metal, and a select still takes 2 instructions. Now, I promised an example where we're going to use two different accelerators, one for matrix math and one for activation function. I'm also going to produce a third version where I can have both the matrix and the activation function together at the same time in the same accelerator. So sort of a fused CXU. So I'm doing matrix multiply, and I've got three nested loops, I, J, K, and I'm doing the regulars multiply and sum operation, followed at the end by a ReLU activation function, which is like a max instruction. If I have just regular scalar code, then the number of instructions per element ends up being 6 instructions. This doesn't have any loop unrolling or, well, it has a little bit of loop unrolling, but not extensive. It doesn't have a vector mode or anything. So there's address calculations and there's loads and stores and loop index calculations. And that's why for each element in the matrix, it's going to take 6 instructions. Now, if we add a single CXU that does both multiply, accumulate, and activation function, we can do a select at the very beginning of our function to select that CXU. And then we issue different instructions. And those go to the same CXU, so we don't need to select. It turns out that we can reduce the instruction count by fusing the multiply add to a single thing. And also the activation function can be a simple instruction. And so we get down to 5.2 instructions per element. However, if we have two separate CXUs, one for matrix multiply math and one for activation function, then we have to select and alternate between those two functions inside our middle loop. There will be a little extra overhead to do those selections. And you see the number of instructions per element is now 5.35 instead of 5.2. So this overhead of the select operation is modest and still faster than the scalar. This is a very contrived example. I would normally want to see custom instructions that do a lot more than just one or two operations. And so we're still seeing a win even with these really simple instructions. So what are some of the takeaways of this? Well, we have an API now that provides a programming model and a state model that all software can use. And it's stable, allows for single binary, stable releases. It's very easy to use. The open returns a selector, which is very similar to a file descriptor that Linux programmers are familiar with. Each library can use an independent selector and keep a cached persistent copy, so it doesn't need to constantly open and close on every function call. And that allows for high performance. And then the selector use automates the virtualization and context switching that's necessary. So user code doesn't have to worry about that. It just gets managed by the operating system. And when the hardware provides more context, then it does less context switching and it gets faster. It's pretty efficient API overall. Selecting between active accelerators takes just 2 instructions. It provides for a lazy context save and restore method in the operating system. So you only save or spill when necessary. And the embedded mode I alluded to reduces the cost of a table lookup. Let me talk a little bit more about a different way of using this. So we've talked about multi-heart and accessing multiple accelerators, but let's look at it from a different point of view. Let's just talk about RISC-V vector as a CX. If I was to create a CX core for the entire RISC-V vector ISA, what would it look like? Well, it would be a whole bunch of instructions, and they'd be assigned to custom opcodes and have custom CSRs. Now, by default, I would have a VLAN of 1024 and 1 state context. What I want to do is I want to provide the option of 2, 4, or 8 state contexts as well without increasing the register file size. So I will subdivide VLAN into smaller pieces. If I have 2 contexts, there'll be 512 bits each. If I have 4 contexts, there'll be 256 bits each. And 8 will be 128 bits VLAN. By having different contexts, it allows multiple hearts to all share a single RISC-V vector core. And if I have 8 state contexts, that means that I could have 8 processes on those 9 cores, all using vector instructions without interfering with each other. Because they have their own state, they do share a single execution core, so it can be very efficient from a hardware point of view. I don't need 8 or 9 copies of the core. I have only a single copy of the state, and it's reduced in size. However, there's something else that comes out of this. I can have a single heart, and that single heart can use this vector core, and it can use all 8 state contexts as though they were hardware threads. So it's a single thread of software on the heart, and it will use the 8 different state contexts to have 8 different instruction queues or 8 instruction pipelines. When you do that, you actually get a performance boost. And the reason you get a performance boost is the vector core is able to see different instructions that are now independent, and it can do a context switch in hardware between those instruction queues on the fly anytime there's a pipeline hazard or a memory latency. So it'll hide memory latency and hide pipeline hazards by pulling in instructions from other state contexts. And you can see this has up to 27% performance boost. So this programming model allows us to share a vector core among multiple hearts, allows us to subdivide the register file into multiple contexts, and we can use those extra contexts to provide increased performance for a single thread or to be shared among multiple threads or multiple processes. So it gives a lot more options than we have currently. Let's look at another possibility. Let's add 2 vector cores instead of 1. And I'll still have 1 to 8 state contexts, but this time I'll actually keep the VLAN the same all the time. So I'll add extra state, just for fun. If we have the same application, then we can take a look at different performance options. So if we have 1 vector core that's these 4 rows of 1 by 1 to 1 by 8, and we get a performance boost of up to 36%. If we have 2 vector cores, 2 by 1 to 2 by 8, we see we have a performance boost of up to 2.66 times. So we get a 2x performance because there's 2 cores, and then we get another 1.33x performance because of the multi-threading at the hardware level by using multiple state contexts. By the way, we looked at another option, which is rewriting the vector code. It's in a way that's very awkward to write, to use prefetching, and we can get 32% performance boost out of that. That gives us hiding memory latency benefits, but we had to manually change the code. It was not automatic. Using these API for multiple contexts, it's the same API. All we're doing is we change 1 loop parameter to go from 1, 2, 4 to 8, and we automatically get performance benefit having the hardware automatically manage the memory hiding instead of having the software try to do it manually. We also did an ideal version where we had memory take every load replaced with a no-op, and the best case performance would be 1.46 in that case. And then we had a scalar version, and of course the scalar version is slower than the vector version by a factor of 4 or 5, depending on whether you look at the cold cache version or the warm cache version. So the bottom line here is CX gives us a way to share vector cores among multiple hearts. We can even have multiple copies of the same vector core to produce higher performance variations on hardware. And the software programming model stays the same in all cases. So just a reminder what CX gives us, a bunch of ISA changes, and then some non-ISA changes. And let me just remind you what those are. If we have custom instructions that don't follow CX, we call those legacy. And you can still use those with CX, and you can go back and forth between them in a seamless way. There is a small change to the API which makes that seamless use a little bit more efficient. but it's not mandatory. Then there's a logic interface part. Whoops, what happened? Oh, sorry. The other thing is the optional logic interface. This is a logic interface between the CPU and an accelerator. There are a bunch of different interfaces already out there. One called ROC for Rocket. There's the Core 5 XIF from Open Hardware Group. There's one called Sky 5. There's a ReRock, which is an improvement on ROC, and so on. And CX defines its own. This allows for modularity so that you can insert a new instruction extension, ideally without changing the CPU itself. You're just talking to a standard interface of the CPU. So you don't have to change instruction decoders and logic inside the CPU. Now, in the case of all of those other instruction interfaces that I talked about, they're not optimized for CX, so there may have to be some CPU changes. But the one we define in CX is designed so that no CPU changes are needed when you add any CX to it. So let's just review what we've done here. We've taken CX and it's given us true ISA liberty for custom instructions. It allows domain experts to design a new instruction extension and assign it a UUID. It allows processor vendors to build a CXU according to that specification. It allows third-party IP vendors to build hardware RTL that builds a modular CXU according to that same specification, and they can license that to multiple different processor vendors. Software vendors, well, we can have a universal Linux kernel driver that works for all possible CXUs doing context save and restore. It also allows for asynchronous execution of these CXUs and allows for migratable hardware threads. It also provides full virtualization and isolation between processes that are using these CXUs. Any library code that's written and optimized for CXs is written to their UUID, which doesn't change. And that can be supported by many different hardware vendors. And so there's a lot of incentive for library writers to optimize code according to popular UUIDs. And then applications build upon these libraries. And the libraries and the applications, they're compiled and updated at different times asynchronously without any concerns. We can have single binary release of an application and of libraries, and it works on all CPUs, whether or not they have a CXU present. Anytime the CPU improves a version of the CXU that uses the same UUID, no software changes are needed to automatically use the improved CXU. However, if we improve a contract and we add new instructions or change their behavior, we need to publish a new UUID, and we do need to do a software library update to use those new instructions properly. So that brings us back to the Magna Carta. Have we provided true democratization and liberty to custom instruction set and provided a free market? I think we have. That's the end of my talk. I'd be happy to take questions.
Thank you very much for the interesting talk. We have time for some questions. One question.
Thank you for. Hello? Can you hear?
Yeah.
Hello.
Hello. Okay. Thank you for your presentation. Very inspiring. What do you think about putting some of this logistics and load in the store in the program loader instead of the same program itself, so that you can manage the security issues and other conflicting extensions?
So we looked at a lot of alternatives, meaning things like recompilation of source and binary rewriting and relinking on the fly. All of them had big problems. And ultimately, we decided the best thing to do was to solve it this particular way, once and for all in hardware at the ISA level, to allow, and we went through a lot of effort to make sure that the Linux kernel driver is the same and doesn't need to be modified every time someone releases a new instruction set extension. So we think this is superior to any other alternative.
More questions? I have one. And what about real applications? Do you know anyone using real applications with your very interesting techniques?
No, we are still in the design stages. We call it a draft CX specification because it's in draft mode. We've produced toy examples ourselves, but it's not to the level where we can do a full application level thing. The closest we have is we've mapped the RISC-V instruction set into this space. So we didn't take RISC-V instructions, we didn't take RVV instructions and give them new custom opcodes. What we did is we took the existing RVV opcodes and just said, let's treat those as if they're custom instructions. And then we steer them all outside to an external interface. And that's the way our particular vector core works with CDA5 and Vectors5. So we've had quite good success mapping the RVV out as a CX. And we think that's a good, concrete, a real application-like example. But we don't have active vector code that can take advantage of the multiple cores or the multiple state contexts like we've demonstrated. We had to produce toy microkernels for that.
Okay. More questions? Okay, so let's thank the speaker again. Thank you, Guy.
Thank you very much.
2 minutes. Thank you very much. The next chair is... Oh, it's the break. Okay, we have the break. Thank you again, Guy. You are not going to have the break with us. You lose a very good dinner yesterday, and you have a break today now.
Oh, I'm so shattered. I would have loved to have been there. I will stay here in case someone wants to privately ask a question. If there's a mic there, I'll stay on for 2 minutes just in case. But feel free to go about your break.
Shy students, it's your time.